Inside your computer right now, there is a volatile environment of billions of electrical charges. They are flipping between high and low states at blinding speeds. There is no inherent meaning here, only physical state. Early programming required engineers to map human logic directly onto these physical states. It meant manually routing cables and setting massive arrays of switches. Code was physically punched into strips of cardboard. You fed the material reality of your instructions directly into the machine. Today, we don't punch holes in cards. We type human-readable text into a code editor. That text is a programming language. It is an artificial construct, a highly structured vocabulary designed to bridge the gap between human intent and that chaotic ocean of bits. In 1995, web pages were entirely static documents. JavaScript was introduced to run inside early browsers, to give those pages basic logic and interactivity. Since then, it has evolved into a ubiquitous computing standard. It powers server-side infrastructure, manages massive databases, and executes logic on nearly every device you own. We are going to build the architecture of a JavaScript program entirely from first principles. We will climb the ladder of abstraction step by step. We will start at raw bits, organize them into values, combine them into expressions, track them with bindings, and finally dictate their behavior with control flow. Mastering this language requires abandoning elementary analogies. We have to observe the exact formal rules the machine uses to allocate memory and manage state. To make sense of the binary chaos, the machine separates bits into discrete chunks. In JavaScript, these chunks are called values. They are the atomic elements of your program. JavaScript uses exactly 64 bits to store a single number value. Because it uses one single bit to indicate a positive or negative sign, the maximum whole number you can store safely is roughly 9 quadrillion. Storing fractional numbers introduces architectural limits. You have to sacrifice some of those 64 bits to store the position of the decimal point. Because of this, fractional math in JavaScript often loses a tiny amount of precision. Text requires a different structure. JavaScript represents text using strings, mapping specific characters to specific numbers via the Unicode standard. The language allocates 16 bits per string element. That gives you enough binary combinations to represent tens of thousands of unique characters across global alphabets. However, the Unicode standard contains far more characters than a 16-bit sequence can hold. Modern editions, like most emojis, actually consume two 16-bit positions stitched together to render a single visual character on your screen. But values alone do absolutely nothing. They exist passively in memory, waiting to be acted upon by operators. A fragment of code that applies an operator to values to produce a new value is called an expression. You can use binary operators to do basic math, or use a ternary conditional operator to pick between two values based on a logical true or false test. The tension in JavaScript's design emerges when you write an expression that combines mismatched value types. Rather than rejecting the mismatch and throwing an error, JavaScript attempts to guess your intent. It quietly converts the values to the types it thinks you need. This is called type coercion. If you multiply the number 8 by null, an intentionally empty value, the engine coerces the empty value into a 0, producing a final calculation of 0. If you subtract 1 from the string 5, JavaScript converts the string to a number, giving 4. But if you add them, the engine prioritizes string concatenation. It converts the number to text, gluing them to output 51. Once an expression produces its final value, that value instantly dissipates. To keep it, you must capture it by altering the structural state. While an expression produces a value, a statement changes the machine's state. It executes an instruction that leaves a lasting mark, known as a side effect. Introductory programming tutorials usually teach you to capture data using variables. They describe these variables as boxes that contain information. This model is flawed. Bindings do not contain values. They are tentacles that grasp them. When you declare a binding with the keyword let, you grow a tentacle that hooks onto a specific chunk of data in memory. When you update a variable, you are not swapping the contents of a box. You are simply redirecting that tentacle to grasp an entirely new value. Values cannot be modified once created. If a value loses all its binding tentacles, it is orphaned. The computer lets it dissolve, recycling its bits for the next generation of data. A program's environment, therefore, is just a real-time map. It is the exact collection of active tethers holding on to data at any given millisecond. By default, the engine reads your statements strictly from top to bottom, traveling in a straight line. Conditional execution introduces a fork in the road. You provide a Boolean expression, a test that evaluates to true or false. Based on that evaluation, the program chooses one branch and completely ignores the other. But straight-line execution fails when you need to process large datasets or repeat a task 1,000 times. You would have to manually type out thousands of identical statements. Looping control flow solves this by bending the path of execution backward in time. Constructs like the while or for loop allow the program to hit the end of a block of code, jump back to the start, and run it again. To prevent the machine from looping infinitely, you create a dedicated binding, a counter. You update this counter's value at the end of every loop until it eventually triggers a false condition at the logic gate, breaking the cycle. Control flow acts as the master routing system. It dictates exactly which tethers move to grasp new values and exactly when they do it. Look at this block of code. It calculates 2 to the 10th power. It starts with initialization. The program establishes 2 tentacles, one grasping the number 1 for our result, and another grasping a 0 to act as our counter. Before it enters the loop body, it tests the counter. Is the counter less than 10? If true, execution proceeds. Here is what happens across every layer at once. The expression multiplies the result by 2. The tether detaches from the old value and grasps the new one. Down in memory, an entirely new 64-bit block is allocated to hold it. The counter tentacle shifts up by 1. The logic gate checks the condition again. The cycle repeats, churning through memory allocations at millions of operations per second. Even highly complex software algorithms ultimately reduce to this mechanism. They are just synchronized loops of values being grasped, evaluated, and left to dissolve. As a program scales to thousands of lines, the interlocking conditions and updating state create an immense, maze-like complexity. If you rely on vague metaphors about boxes and data, you will get lost in that maze. A mechanical understanding of how memory is allocated and how tethers tack that memory keeps the logic grounded. JavaScript functions as an active state tracking system. It is a live architecture managing thousands of tiny, rapid changes within the machine. Programming requires defining the exact rules of engagement. You are taking human intent and translating it into the silent, invisible, and flawless logic of the machine.